Hi. So in the previous experiment, the book had us use one of these, a classic 555 timer IC, to set up a simple oscillator to create a tone in a loudspeaker. And we modulated that tone with one of these. Now, at first sight, this might look like an ordinary LED with a clear packaging, but in fact, it's not an LED, it's a phototransistor. And this transistor operates in a similar way to this, which is a classic bipolar junction transistor. The difference being that this has three leads, it has a collector and emitter lead, and then it also has a base. And it is in fact the current applied at the base that controls the collector and emitter current. And this one, the phototransistor, works in a similar way, except that it just has leads for the collector and emitter, and what controls the current across them is in fact the amount of light falling on the transistor. Now, if you've been following this series so far, you'll know that the book has been encouraging us, rather than just relying on datasheets for these types of components, to find out a little bit more about their characteristics through experimentation. And in fact, we did that for this, which is the PN2222 bipolar junction transistor. We did a simple experiment to just find out some of the characteristics. So in this experiment, the book has us doing a similar thing. Firstly for this, which is the PT334-6C Phototransistor, and then finally for our classic 555 timer IC. So let's start off first by building the circuit that the book suggests for measuring the characteristics of the phototransistor.
So I just want to explain the setup I've got here. So here's the circuit board. It has the 5-volt regulator, the same one that we've been using. The only difference is that I've removed the little LED indicator because that will skew our results, because obviously that generates light. And then I have, and I'll show you this in a bit more detail in a moment, but I basically have the phototransistor in series with a 330k resistor to create a voltage divider. And I am measuring at the moment the voltage across the resistor. Now I have the power lead for the regulator and the leads from the meter coming through the walls of a sort of makeshift cardboard box here. The idea being that what I can do when we start to make measurements is effectively shroud the breadboard so that we can still see the meter, but that the breadboard is in this dark environment. Now, obviously, this is a cardboard box. It's not a precision piece of apparatus, so it's not going to be a complete light seal. But what it will do, I hope, is give me a consistent low light level for some readings. So hopefully you can see this a bit more clearly now. So it's still a bit difficult to see on the video because it's got a translucent body, but here's the photo transistor, and that's connected in series with a 330k resistor. And then at the moment we're measuring the voltage across the resistor, and you can see it's kind of dancing around a little bit, but we're getting around about 4.8, 4.7 volts. So now let's see what happens when I lower the shroud to cut off most of the light. Let's just get these leads out of the way, and you can see that's dropped right down. We're getting 0.014 of a volt there. And again, if I lift it back up, then you can see that's gone right back up to 4.8. So what I'll try now is just putting the indicator LED for the voltage regulator back, and that should give us a slightly higher level even when we lower the shroud, because of course we will then have a little bit of light going on inside the box. So let's try that. Right, so there's our LED. So again, we've got a reading of 4.8 approximately. So let's now just lower the shroud again and see what we get. And you can see there we're getting, it's still very low, but it is a little bit higher than it was without the LED, so 0.0293. So what you can see there is that with this wiring, that the amount of light falling onto the phototransistor is increasing the voltage. What we should see, if we swap the position of the phototransistor and the resistor, is that the opposite happens. So let's see if that is indeed true. So this time you can see with the full amount of light falling onto the phototransistor, now that the positions of the phototransistor and the resistor have been swapped, we're getting quite a low voltage reading there. Obviously it's varying because I'm moving my hand around and that's changing the level of light falling on it, which is why we're getting that variance. But if I just sit still for a moment, hopefully that will stabilize a little bit. So we're getting about 0.15 of a volt across there. So let's now again once more try lowering the shroud over the circuit, and there you can see that voltage level has gone up to 3.5 volts. So we are indeed getting the opposite happening, that as the light level is reduced, the voltage is increasing, which is opposite of what we saw in the previous configuration. And again, as I add that light source back in, that voltage drops back down again.
Okay, so now we have some figures for the phototransistor. Let's move on to the 555 timer IC. Now, I'm assuming in this video that you already have some familiarity with the 555, either because you're already at a level where you've encountered 555 circuits and understand how they work, or perhaps because you worked your way through the first make electronics book, which covers the 555 in some detail. And so assuming that you fall into one of those two categories, you will know that the 555 has three primary modes. Now, one of those modes, the bistable mode, we're going to ignore for this experiment. So we're going to focus on the two timing modes, and the first of those is the monostable mode. In the monostable mode, pin 3, the output pin, is normally in a low state, while the trigger pin is normally in a high state. But when the trigger pin is brought low, that will begin a pulse of high output at pin 3, and the duration of that pulse is going to depend on the values of the components in an RC circuit attached to pin 6, the threshold pin, and pin 7, the discharge pin. So what we're going to do for this experiment is set up a simple circuit shown in the book to measure the duration of those pulses, and then we'll experiment with different values of components to see the effect they have.
Here's an initial version of the test circuit, and you can see I've got the usual power arrangement set up here for the 555, which is the ground into pin 1, and then the 5 volt regulated supply is going into pin 8. Then I've got the RC circuit. I've started off here with some fairly high values so that we can see the pulse. So there's a 330k resistor and a 10 microfarad capacitor. What might not be immediately clear on the video is that there is actually a tiny little link here between pin 6 and 7, so that they're both being fed by that RC circuit. Now, I'm not making use of the control pin, pin 5, so that is going to ground via a small capacitor to just block any noise. I'm also not making use of the reset pin, pin 4, so that is held high with the connection to the positive supply rail. Now, the output is going to the oscilloscope probe so that we can measure it. Now, you might be tempted, if you're building a test circuit, to do what I've done here, which is for pin 2, the trigger pin, to normally be held high using this pull-up resistor here, and then to have a button to connect it to ground so that you can trigger it manually. There is a problem with this simplistic arrangement though, and it's a problem that may not be immediately apparent when you start to use it, and let me show you why. And here you can see the oscilloscope trace. At the moment we're getting a flat line because the output from pin 3 is low. But if I press the button to trigger a pulse, there you can see the start of the pulse. It's going high for a while, and then it's lasting for, these are about half-second increments, so 1, 2, 3. It's lasting for about 3 seconds before dropping low again. So you can see everything seems to be working as it should do. But let me now just swap out the components in the RC circuit for some smaller values, and you'll see what the issue is. So I've now swapped out the RC components for a 10k resistor combined with a 0.1 microfarad capacitor. So let me just try the experiment again. So I'm going to press the button to trigger the circuit. There you see a briefer pulse. Now I'm going to do it again. Okay, you should immediately see that there's an issue here. The length of this pulse is clearly much shorter than the length of this pulse. So what is going on here? Why is our circuit suddenly starting to misbehave? Well, here's the issue. Let me start the trace running again. And this time I'm just going to keep the button for the trigger held down. And now I'm going to release it. So there you have it. You can see that as long as that button is held down, then the circuit remains in a high state. And clearly that's not what we want. That's going to completely skew our timings. So what can we do about this?
To solve this, we can use a characteristic of capacitors that was also introduced in the Make Electronics book, which is capacitive coupling. So we're going to change our simplistic circuit to one that looks like this. You can see here that the trigger pin is now connected to a capacitor and both plates of the capacitor are connected to the positive supply rail via pull-up resistors. The button is now connected to the opposite plate of the capacitor to the one connected to pin 2. The other side of the button is connected to the 0 volt rail via a pull-down resistor. Now when we push the button, the left plate of the capacitor is pulled low, which because of capacitive coupling causes the right plate to go momentarily low before quickly recharging. This brief negative blip is enough to trigger the 555. And now, if we were to hold the button down, this would not have any impact on the length of the pulse. So let me build this new circuit and see if this works for us.
So now, when I press the button, we get our pulse. If I press it several times in succession, you can see that each of those pulses is a consistent width. So that does seem to indicate that this new circuit is doing exactly what we want it to do. But let me just make sure, and this time what I'm going to do is start a pulse, but I'm going to hold the button down. And there you can see I just got a single pulse showing on the oscilloscope, and even though my finger is still on the button, that pulse has ended long ago, and I'll have to release the button and press it again to start a new pulse. And no matter how long or short I hold the button, all it does is affect the timing of the start of the pulse. It has no impact on the duration of the pulse. So that is working as we expect. And what I can do now, if I just freeze a pulse on screen, is use the cursors to measure the width of the pulse. So let me move the A into there. And just change over to the B line, move that across. And so that is giving me a duration of 0.114 seconds. So what I can do now is, now I know that the circuit is working correctly, is reset the experiment, changing over the values of the RC circuit and record a series of measurements to see the impact different values of the RC circuit will have on the pulse duration. So I'll do that now and then I'll come back and show you the results. So here's a small sample of results I obtained from testing 5 different resistor values from 10k to 1 meg, each against 2 different capacitors with values of 1 microfarad and 10 microfarads respectively.
What you can see from these is that the period of the pulse can change dramatically even with the same capacitor just by changing the resistance value in series with it. The book has a table with typical pulse durations for a much wider range of capacitance and resistance. Okay, let's now look at the second timing mode for the 555, the astable mode. Rather than a single shot pulse, this mode creates a consistent periodic signal at the output pin. In other words, it acts as an oscillator. The secret to this is a feedback loop from pin 6, the threshold pin, to pin 2, the trigger pin. As the capacitor in the RC circuit discharges, it pulls pin 2 low, triggering the 555 and starting another charging cycle. Another thing to note is that this circuit has separate charge and discharge paths. It's possible to change the duty cycle of the pulse wave that's created. Okay, I'll now build this final circuit of this episode.
So I've built the circuit, this time in the astable configuration. And once again, the best way to measure the output is to use an oscilloscope. So if I power the circuit on, immediately there we can see that square wave. And down here we can see we're getting a frequency of 46.26 hertz. It's dancing around a little bit, but it's gone up a little bit now to 46.38 hertz, and it seems to be settling there. So this is the easiest way to measure the frequency, and this particular frequency we're getting from two 10K resistors and a 10 nanofarad capacitor.
So I hope you found that interesting. In the next experiment, the book continues with the theme of audio oscillators using the 555 timer IC. But in this case, rather than using a phototransistor connected to the control pin to modulate the output, we're going to use a signal from a second 555 timer IC. So please do join me for that in the next video. See you then.